everyone, and welcome to our monthly webinar that has been proposed by our BCS branch in Cheltenham and Gloucester. We have today Zainab, which is one of the treasurer, or which is the treasurer of our BCS branch, and it is with us today, and it's going to give an amazing, very good talk on deep learning applications for object detection in robotics. Zainab, off to you.
Thank you. Hello, everyone. Hello, Tiago. Thank you for your introduction. Shall I share my screen? Just to confirm that you can see it.
Please.
Can you see my screen?
Not yet, Zainab.
Okay. What about now?
Sorry, still not seeing your screen. I'm sorry, Zainab.
Okay. And now? So the show screen is on from my side. I don't know if everyone else can't see my screen.
Oh yes, now it's loading. Thank you, Zainab. So now it's all good to go. Once
Okay,
again,
perfect.
For the talk, and let's start.
Thank you. So hello, everyone. Let me just introduce myself. I am Zainab Lukil. I am the treasurer of the Gloucester and Cheltenham BCS branch, and I am lecturer in computer science at the University of Gloucestershire, and I am part of the cyber and technical computing department. Also, I am a PhD researcher at the same university, and I'm working on artificial intelligence and medical image processing that I am going to talk about my background in a minute. So today I'm going to talk about my future directions in terms of research and the research that I am aiming to work on, which is object detection using deep learning in robotics. This is the summary of today's talk. So I'm going to start with the knowledge and experience related to the area of deep learning, a bit of introduction of the subject that I'm going to talk about today, the difference between object localization and the object detection, 3D object detection, and here I'm going to focus on the camera geometry and how your camera sensor will detect 3D objects. Deep learning evaluation metrics for object detection. I'm going to talk about a set of important parameters that will evaluate your deep learning model and will reflect the accuracy and efficiency of it. Also, I selected 3 different research papers, recent ones, about object detection using deep learning in robotics. And from that, we're going to extract some challenges and some maybe future directions that we can focus on future researches as well. So let me start with my knowledge and experience related to the area of AI and data processing. So when I started my research career, I started with a placement at the University of Gloucestershire, and I worked on the design of a deep learning approach for brain data pre-processing towards bias and non-bias of situation awareness. And here I used the artifactual data, EEG data, as an input to my model. And the main blocks or the main model that I used for the deep learning approach is the deep auto encoder, or what we call DAE. This work was a part of the neural network analysis of brain activity underpinning information processing and situation awareness, the Open Mind project, in collaboration with the School of Science as part of the University of Gloucestershire. So this framework summarizes the deep learning deep learning based approach that I designed as a result of that placement, and we submitted the journal paper to an IEEE paper, and we are still waiting for a feedback. Also, I published a conference paper in 2020 on the design of a new hybrid deep convolutional neural network for medical image processing. My network, or my hybrid network, is called Denseception, and it is basically a combination of DenseNet network and Inception network architectures. So the mixture between these two construct the hybrid network, which as a result, constructing a hybrid dense block, hybrid transition block, and hybrid composition of each of these blocks. The hybrid dense block is basically a combination of convolutional blocks and inception blocks, including the inception A and inception B. And this will construct a very dense connections between these different items that will help into extracting more efficient and more reliable features out of the image that you are processing. And one of the advantages of my hybrid network is that you can generalize it not only for medical image processing, but any other type of image that you can use in your research. Also, the hybrid transition block architecture is a mixture between reduction blocks and convolutional blocks. And as it's known about the reduction blocks, it is minimizing the unuseful or unwanted data out of the input data that will, first of all, minimize the time processing, which is a key element in deep learning and big data analysis. And also, it will increase and enhance the accuracy output or outcome of your model, of the final processing model. So this is an overview, a quick overview about the previous works that I've done so far. Currently, on my PhD, I am working on designing a new framework for DME prediction based on 3D OCT images, which are the 3D eye images. This is just a quick introduction and quick summary about the research that I am doing. So I'm aiming to implement a scalable and automated hybrid deep learning based framework. The framework is designed to ensure an investigation of different deep learning approaches, architectures, towards constructing an efficient outcome out of these approaches. So the model conception will link the target disease and will actually learn features from the related 3D images, particularly the OCT images of one patient, and generalize it onto a set of patients. So this research is currently still ongoing, and hopefully when we get to the final submission of my thesis, we can have another maybe presentation of my about my PhD research. However, for today, I wanted to talk about the future research that I am interested in, and I'm really aiming to allocate my research time based on the deep learning for object detection in robotics. I really find this area very interesting, and especially in the specific field that I am focusing on, that is mushrooms and tomatoes. It might seem like a bit weird of mushrooms and tomatoes. What is the relationship between mushroom, tomato, and robotics? We're going to explore that today together, but it's really, really an important subject and area in object detection that is crucial, challenging, and really interesting as well. So during the last years, there has been a rapid and successful expansion on computer vision research. Parts of this success have come from adopting and adapting machine learning methods, while others from the development of new representations and models for specific computer visions, or from the development of efficient solutions. One area that has attained great progress is actually object detection. So given a set of object classes, object detection consists in determining the location and scale of all objects instances, if there are any, that are present in an image. Thus, the objective of an object detector is to find all object instances of one or more given object classes, regardless of the scale, location, the pose, the view with respect to the camera, and the partial occlusions, and also the illumination conditions. So all of these are related to the object detection, which makes it really challenging. In many computer vision systems, the object detection is the first task being performed as it allows to obtain further information regarding the object, the detected object, and about the scene in general. So once an object an instance has been detected, let's say face has been detected in the image, it is being possible to obtain further information, for example, recognizing the specific instance, for example, identifying the subject's face, tracking the object over an image sequence, so tracking the face in a video, for example, and extracting further information about that particular object, particularly what is the gender of that object based on the face recognition. While it is also to first infer the presence or location of other objects in the scene, let's say a hand, for example, near a face at the similar scale, like both of them, they have the similar scale. This can be challenging for your algorithm to detect only the face. And second, better estimating further information about the scene. For example, the type of the scene, is it indoor or outdoor, and also among other contextual information. So it's really, really, really interesting how object detection is a challenging area and challenging task to do, especially in relation to AI-based models. The object detection has been used in many applications, like with most popular ones, including human-computer interactions, or what we call the HCI, robotics, for example, service robotics or service robots, consumer electronics, for example, smartphones, security applications like recognition, tracking. There are also retrieval applications like search engines, photo management, and also transportation applications, including autonomous and assisted driving, which is really an interesting area as well. Each of these applications has different requirements, including, let's say, processing time. Are you doing the processing time offline? Are you doing it online? Are you doing it as a real-time processing? Also, the robustness to occlusions, so how robust your model will be in regards of all of these challenges. The invariance to rotation, for example, if my model will see my face like that, if I flip the face, can the program still recognize me? This is really important to consider as well. the detection under pose changes. So if the pose changes, the angles, the translation, all of these parameters are really important to consider in these applications. While many applications consider the detection of a single object, like a single object class, for example, a face or I don't know, a vehicle or a human or an animal like a cat or a dog, and from a single view, like for example, frontal faces, frontal view, other applications require detection of multiple object classes. So in one image, you need not you, obviously, your model needs to be able to detect different objects like humans, vehicles, animals, and maybe vegetables, why not? Or of a single class from multiple views. So you can focus on humans, but humans from multiple views and multiple poses. So in general, the most systems can detect only a single object class from a restricted set of views and poses. And this is really representing one of the most challenges in object detection area. So this is the robotics for object detection. Robots can see, analyze, and make decisions, more likely like humans every day. And it's really getting interesting how robots can do all of this. And this is obviously thanks to the advances in covering technologies like artificial intelligence, machine learning, and computer vision. Developing such visual analysis logic involves implementing solutions that can determine the orientation of objects, dealing with moving objects, performing navigation as well. Actually, the foundation of this kind of application starts with two very important tasks. The first one is the pre-processing of the data. So when you have your data collected out of your robot, you need to do a specific data pre-processing from the real world via sensors to get into a more usable state by various systems or subsystems, which means how your robot or how your system implemented will actually translate or pre-process what's in the real world representation into a more visible and more understandable by the computer system. Secondly, is to perform feature detection and extraction of visual features from the data, such as corners, edges, and multiple other features that can be involved and can impact on the outcome of your model. So it's really important to consider these two major tasks in object detection using AI-based or machine learning, deep learning, computer vision-based models. So once these systems are in place, so you can move on to the higher level robotic vision functionality, namely object detection and classification, and also object tracking and navigation. So in the following section, I'm gonna talk about object localization and object detection. The first question you will ask, okay, what is the difference? Or why you are highlighting these two different, let's say, items? It's very important, again, to understand what is the difference between these two, because it will help you into developing a multi-class object detection system and not only one or single class single class detection system, and also about the multi-viewing criteria that not all the current systems are taking it as a serious parameter. So this is my mushroom. So you're gonna see this a lot alongside the coming slides. So it's a very beautiful mushroom, and it's detected as a mushroom, okay? And I have another picture, the right one, that has mushrooms again, and also it has tomato. So tomato and mushrooms in one image, the right one, and mushroom in the left image. You would say, okay, thank you very much. We know this is mushroom with this tomato, but what are we gonna do with this? The area that I'm interested in object detection is actually designing or implementing, creating a robot that is able to pick and pack mushrooms efficiently. Why mushroom specifically? First, because it is a very sensitive object, and it has a lot of shapes, it has a lot of colors, and if I see it from multiple poses, it might be detected in the wrong way, so misunderstood, or it's kind of false positive kind of detection. So this is the area that I'm interested in, and that's why I'm using tomato and mushrooms. So don't be like saying, oh, why she's talking about them just now. Okay, so the difference between these two images is that the left image has one mushroom, and it has like a blur background, so we can't really see what's going on in this side. However, the right image, it has two different objects, clear visible objects, which are the mushrooms and tomato. So the difference between object localization and object detection is that the object localization simply aims to locate the main or most visible object in an image, while the object detection tries to find out all the objects and their boundaries within the image, which is a more complicated process, and it needs more features extraction and more parameters to be involved in the training of your system. So how we do, or do we do, object localization? Obviously, we're going to have an object localization system that will tell me, Zainab, this is a mushroom. It's a mushroom detected. How this can happen, and how my algorithm will actually detect or localize that there is a mushroom within my image. Here, we need to talk about what we call bounding boxes. Bounding boxes will help into creating a coordinate system that will tell that in here, in this specific area, a mushroom is detected or a mushroom is localized. Normally, with the AI-based models, we will not have the exact same boundaries, the exact same bounding boxing, because this is very perfect, like it's actually localizing where it is exactly. But we're gonna have what we call predicted bounding boxes, and we have multiple methods to detect and localize the object in the image. Okay, so now we have a clear vision about the object localization, but how we do the object detection then? So how do we generalize this for multiple objects? Imagine again with the right image that I used with tomato and mushroom, how I'm gonna use the bounding boxes in order to detect multiple objects. With a single object is straightforward, it's very easy. But with multiple objects, with multiple views, multiple poses, it can be really challenging. The first method that we can use is called sliding windows detector. So the sliding windows play an integral role in object classification, as they allow us to localize exactly where in an image an object resides. Utilizing both a sliding window and an image pyramid, we are able to detect the objects in an image at the various scales and locations. The second method that we can use for multiple objects is the single shot detector, or what we call SSD. So the single shot detector is like YOLO, YOLO, which is you look only once architecture that takes only one shot to detect multiple objects that are present or localized in an image using a multi-boxing method. And it is significantly faster in speed and high accuracy object detection algorithm. The third method that can be used for multiple objects is called regional-based detector. So the regional-based detector is actually using the regions of interests, or the ROI, for object detection. And based on these ROI pooling, the method takes every region of interest from the input and takes a section into the feature map, which corresponds to that particular regional or region of interest, and converts that feature map section into a fixed dimension map. Now you can ask the question, okay, so we have these three different methods that we can use in multiple object detections that we can implement within our system. But how do I know which one is better? How do I know that that particular method will give me actually a better accuracy or a better efficiency? Actually, testing is a key. So it depends on the data that you are using. It depends on the system that you are building. It depends on the outcome that you are working towards. So a lot of parameters that need to be involved in order to select one of these methods. Some of the applications with a particular data set will be efficiently detecting multiple objects by using single shot detector. Some other data sets will give you a better accuracy when you use regional based detector. So it's really not a straightforward answer. It needs testing first, and it needs to have a clear vision about the data and the program you are implementing. Moving now to the 3D object detection section, and as I mentioned in the beginning, I'm going to talk about the camera geometry model, and particularly I'm going to focus on the pinhole model. So the pinhole model is a presentation of the simplest presentation of the camera geometry model that describes the mathematical relationship of the projection of points in the 3D space onto an image plane. So how to migrate, how to go from a 3D representation from the world system into actually the image plane system. So as you can see here, again, we have a new mushrooms, which is good. So I'm not using the same image. Again, here we have a different shape of a mushroom with a different color, with a different like dots on top of it. So your model might be a bit confused if you change the object input. That's why the interest that I have on mushroom particularly is really important to consider, because the different shapes, the different colors, the different poses that the mushroom can have can affect the final outcome of the model. So simply, this is a very basic model. So we have the 3D object detected. It goes through the lens and detected by the sensor, and it will be flipped and reduced by the focal distance f. So as I said, migrating from the 3D world coordinate system into a 2D image plane system, it needs a lot of mathematical relationships. And one of the key points that you need to consider when you are designing your robotics application, this is a key point that to consider throughout the development. So from the world coordinate system, we're gonna go through the camera coordinate system. And from the camera coordinate system, it will do a projection on the image coordinate system. And the image coordinate system will be used as an input into your AI-based model. That's why it is really important to understand and to efficiently understand how this process is being done and how the mathematical model is being built up. So first of all, we start from the projection of the world coordinate system into the camera coordinate system. And here, two parameters, two extrinsic parameters are important to mention, which are R and T. R for rotation and T for translation. So as you can see here, the camera-based frame vector is equal to the multiplication of, the matrix, which is based on the rotation and translation vectors times the original world coordinate system vector. So this is the first step your sensor will do. The second step is to migrate from the camera coordinate system into the image system. So the image system has a image frame in between, which is represented by small x and small y coordinates. So this is a very straightforward mathematical relationship between the camera coordinates and the frame coordinates x and y, and it will lead to the multiplication of a matrix based on the focal distance f and the camera coordinate system based vector. The final conversion is into the image plane coordinate system. So from image plane coordinate system into the pixel coordinate system, which is UV. The mathematical relationship between these two different 2D systems is based on the derivative of x-axis and the original points O of the pixel coordinate system, which is U0 and V0, and of course multiplied by the image plane coordinate system xy vector. So to summarize all of this, we have two different convergence or coordinate system convergence. So we have the world from world coordinate systems into camera coordinate systems, and here we are talking about extrinsic parameters including rotation matrix and transition matrix. And we have the second conversion, which is from camera coordinate system into the pixel coordinate system, which will your computer system will use as data preprocessing and analysis. Within this conversion, we have what we call intrinsic parameters, including the intrinsic metrics, the focal length, and the optical center, because it's based on the focal distance metrics. To summarize all of these conversion, this is the model that we're going to use as a conversion from the world coordinate system into the pixel coordinate system. So we're going to use A. So A is represented by the intrinsic parameters, including this part of the equation. Also, RT matrices as intrinsic rotation and translation matrices, matrices, and then the final parameter, which is capital X, which is the world coordinates system. So it's a bit straightforward relationship on how to go from a 3D world object detected into a pixel representation. But in real life application and how you can implement this within your system to consider multiple objects in one single image is actually challenging. And this is what I like about this area of research, really. So one of the important parts that needs to be considered in the implementation or design of your system is actually to evaluate the metrics of your object detection. And I'm always having conversation with my supervisor about how we're gonna evaluate our system, how we can say that this particular model is actually accurate or efficient. There are a lot of straightforward, well-used matrices or evaluation metrics that are being used in order to evaluate deep learning-based models. But it's really important to select the adequate evaluation parameters that will actually reflect the efficiency, sensitivity, and specificity of your model. And this is how your object detection model will be considered as an accurate resulted model. One of the metrics that is being used for object detection is the intersection over union. So as its name saying, it is actually based on intersections and unions. But the question is between which parameters, like between which part of this particular image. So it is actually the difference between the human annotated box, which is the correct box that you can see here on the image, and the predicted box out of your deep learning based model. So your model, as I mentioned in the beginning, it will not give you, well, it can, but in general, it won't give you the exact location of your model, like we can see with the correct annotation. So it will give you the highest possible prediction score that you can use to say, oh, this is a mushroom and this is the localization of the mushroom. So the intersection over union, it's actually measuring or evaluating the object segmentation and detection applications. That's why it's firstly detect or extract the intersection area between the correct and predicted boxes, and also calculating the union between the correct and predicted boxes. As its name saying, intersection over union. So we have the area of intersection divided by the area of union, and this is the result of the intersection over union parameter. So here we need to specify a threshold of bounding boxes evaluation decision. However, how we get the intersection, how we know that this is actually the intersection, and this is a really important and a tricky calculation. So it needs to be very specific in order to give you the actual efficiency of your predicted model or predictive model. The first thing you need to do is to design two different, let's say, variables, okay, that will have, or vectors that will have the actual coordinates of your system. When I say coordinates, here I am talking about pixel coordinates, because we went already from the 3D object detection and how these convergence are being done through the camera-based sensor, and then what is the output of your system to be analyzed and produce the outcome at the final stage. So x1, y1, x2, y2 for both boxes. So box 1 is for the predicted and box 2 is for the correct. First thing you need to do is to calculate the maximum of the x1, y1 of both boxes. In this case, the maximum is the top corner of the green triangle, sorry, not triangle, rectangle. And the second step that you need to do is to calculate the minimum of x2, y2. In this case, it is the lower corner, right corner of the predicted box. And that's how we extract the intersection between the predicted and the actual or correct box. The second parameter is the non-maximum suppression parameter. And the non-maximum suppression parameter is used to select the most appropriate bounding boxes or bounding box for the object from a set of overlapping boxes. So as you can see here, to calculate the non-maximum suppression, I need to generalize or generate multiple overlapping boxes. The first thing that I need to do is to select a threshold. Normally it is 0.5, just to make life easier. And then you clean up the bounding boxes. By clean up, I mean removing all the unwanted or the boxes that are not actually representing the object. And then you assign, not you, your algorithm will assign different scores or confidence scores for your boxes. So as you can see here, I gave this box 0.9, a second box 0.7, and the final box is 0.53. What I need to do first is to select the maximum confidence score and then compare it with the rest of the scores. If the intersection over union parameter is above the threshold that I already set it up, then I eliminate the box with a minor score. And I do the same with the remaining boxes. Same, comparing 0.9 and 0.7 intersection over union parameter with the threshold, it's above it. So my final box is the box with 0.9 confidence, which makes sense because it is a true positive box. The other ones, especially the 0.7, it is considered as most part of it is considered as a false positive and not a true positive. Now, back into tomato. Imagine we have a tomato with the mushroom in the same figure. How are we gonna do this? It's exactly the same parallel process, generating overlapping boxes, and off you go. You have your threshold. The program will generate the confidence values, and then it will extract the most appropriate box. The third parameter, which is one of the most important parameters, which is the mean average precision parameter. Excuse me. So on the left figure, which is image number 2, we have our friend mushroom, again with the same picture, so I didn't change it this time. And this image number 1 on the right side, we have multiple shoppings done on this image. So we have tomato, mushroom, lettuce, and spring onions. Excuse me. So what I'm going to do with these two images, let me just define what is the average or the mean average precision. So it is basically based on the intersection over union metric, where the values are varying from 0 up to 1, and it is known as the confidence value, where 1 is the optimal result. Like if your algorithm will give you a 1 for a particular box, which means it's the exact box, as you can see here, the green ones. But obviously, these green ones are done manually. So they are done in order as a target or clean data that you can use to evaluate your system. However, normally and always we work with predicted boxes, and this is how your algorithm will make sense and make value. As a summary, the intersection over union score measures how close is the predicted box to the ground truth box. So the ground truth box is the green box, and your predicted box will be the red boxes. So when the intersection over union is greater than the threshold, then the box is classified as a positive as it surrounds an object. But this is not all the time, because, for example, this case, this 0.8 here, it is supposed to be for tomato, but it's actually having just a small part of the tomato. I'm saying is 0.8. You say, oh, fantastic. So it actually detected the tomato, but it's not. It's considered as a false positive. However, with a 0.9 here, we can see that most of the mushrooms are within the box. So the mushroom is successfully detected. 0.6 here is just an empty space that is being detected. So it is actually a false positive. Same for the spring onion, because we are not looking for the spring onion. And this will lead me to emphasize on the challenging way that when you work on object detection with a picture that has a lot of objects and you need to focus on a particular classes of objects, is really challenging and might affect the accuracy and efficiency of your algorithm. And for example, in this case, predicting this area is useless because it's not covering neither the tomato nor the mushroom. Same in here in the left picture, we have the box with 0.7 confidence. It's actually representing most of the mushroom in it. And we have the other box, which is represented by 0.2, which also makes sense. So the prediction on the left side is actually good. What we need to do in order to measure the average precision, first of all, we need to design or setting the bounding box predictions. So first of all, you have the image, the different boxes that you have predicted, the confidence that your algorithm gave to your boxes, and then each one, what is the false positive and what is the true positive, as I just demonstrated. Then you need to sort these predictions based on the confidence metric. So in here, my top confidence metric is 0.9 and the lower one is 0.2. And the true positive and false positive presented by TP and FP remain the same. What we need here, when we talk about false positive and true positive, we are talking about the confusion metrics, where it has FP as false positive, TP for true positive, TN for true negative, and FN for false negative. The two major key parameters that we can extract are precision and recall. So the precision is represented by the intersection of M and J, M and G are presenting predictions and ground truth respectively, divided by the whole amount of predicted elements, which is representing, based on the confusion metrics, the true positives divided by the false positives and the true positives. The recall is the division of the interception J, which is the prediction and the ground truth, representing the true positives, divided by the ground truth, represented by the true positives, plus or and the false negatives. So these two parameters or metrics will lead into the measure of the average precision or MAP parameter. Backing to our table, so we already have the confidence and TPFP already filled. Now we calculated the precision and recall for each detected or predicted box. The following step is to design or display the precision recall graph and area under curve or AUC graph, which is the precision with relationship with the recall parameters. In our particular application, the mushroom average precision was 0.74, which is really good, and this is thanks to the if I go back here, the 0.9 box, which has been detected, and also the 0.7 here, which has been detected as well. However, with the tomato average precision, we got only 0.533. So imagine here, I have only mushrooms in my images, and I don't care about tomato or any other object. My overall average precision will be 0.74. However, because I am focusing on multiple objects, multiple classes in one particular image, I am actually minimizing or decreasing the resulted average precision, which will cause it to be, instead of 0.74, I will have it as 0.6365. So the tomato misdetection impacted the final outcome of my evaluation metric. So it's really important to consider what are the objects that you are detecting, how you are detecting them, what are the actual features that you are, considering in terms of posing, views, elements to consider, and so on. So yeah, this is all about the metrics evaluations. There are a lot of other metrics that we can use in order to evaluate, measure, or evaluate the actual performance of the deep learning based model, but these are the three different parameters that I selected for today's presentation. Now we come to the final part of today's presentation, which is about the three different researches that I selected, which have been recently published in relation to robotics with deep learning approaches for object detection. The first paper that I was interested in is the deep learning object recognition for robot picking task. Picking task is one of the features that I'm planning to include in my future research. So what is their method? So they applied deep learning approach, particularly ResNet's 150 CNN network, and they used semantic segmentation in order to converge into an accurate algorithm for object detection in a cluttered scene and to help the robot to actually pick up the correct object in cluttered environment. So it sounds really challenging and interesting. Why they did this? So first of all, failure of classic algorithms to detect objects having no texture, and therefore the need for deep learning techniques. So the classic techniques couldn't solve the no texture parameter of the objects. How they did the implementation and how they did actually the object recognition. They first implemented their deep learning-based model, which is the ResNet 150 for semantic segmentation. So they did the segmenting of the object accurately that makes the picking task easier. They used 2D images reconstruction, so it's not 3D. These are the software that they used. And they did like a comparison of their model with the existing one, which is YOLO. This is their framework that you used. So their input is based on RGB image with object in cluttered scene. And here, another input, RGB images containing object in cluttered scene plus binary mask. And both of them are fed into the CNN ResNet in order to output a binary mask of that particular object. When they did the comparison, which is a very and fundamental stage that any research needs to cover, is comparing what you've got with the existing ones. So as you can see, their intersection over union parameter is nearly double the intersection over union of YOLO. So as we can see, ResNet 150 presented a more object detection performance compared to the YOLO. So in case of cluttered picking, this is the summary that we can extract from this particular example. In case of cluttered picking, semantic segmentation performs better than bounding boxes that I talked about. Example number 2 is real-time object detection and recognition on low compute humanoid robots using deep learning. So what is their method? They developed a fundamental technology using deep learning approach, particularly the YOLO version 3. Why they did that? So to enable robots to detect objects and recognize them for effective manipulations and take real-time decisions, including those objects. So their approach is basically working on real-time decisions of detected objects. How? First of all, they modified the original YOLO version 3 architecture for detection of objects in robots camera view and take programmable actions based on the detected objects. So it's really challenging tasks. So you are doing the actions based on real-time object detection. And you can imagine the error rate that can happen and how accurate this algorithm should have been in order to provide accurate results. They do quantization of the weights of the different parameters and readjustment of filter sizes within the YOLO architecture, and also they did the reduction of the number of filters per convolutional layer of the YOLO composition, YOLO architecture composition. Again, they use 2D camera space, and their modified YOLO version 3 performances is actually in the average precision, it wasn't better than YOLO version 3. The mean inference time, which is another parameters, it was less than the actual YOLO version 3. So the improvement of the inference time for low resolution images from the robot's camera feed, which is really important. As a future direction, deep learning approach for 3D space object detection using depth sensors. So the depth sensors would help better than using 2D camera sensor, especially in real life applications or real-time applications. The final example, which is a bit similar to what I am aiming to go, not similar in terms of model or framework, in terms of the pick and place operations. So it is about deep learning based object classification and position estimation pipeline for potential use in robotized pick and place operations. Their method is based on the development of an accurate object detection and position estimation algorithm using CNN approach. The reason why of this development is the design of autonomous pick and place operations. So they use the RGBD sensors, which are RGB and depth sensors images at the same time. They used a combination of 3D point cloud processing using PCL. They did a modification of the basic CNN by adding a fully connected layer followed by a softmax layer at the end. And also they compared their actual 3D CNN approach with existing CNN architectures like Fusion CNN and Original CNN, plus the VGG 3D architecture. They used ROS for robot manipulation control software. So this is a mathematical representation that describes the relationship between the RGB image, the depth image, and the encoded label. This relationship between RGB image, depth image, and encoded label is translated by the likelihood function L, and they tried to minimize L in order to obtain more valuable or more accurate system. So minimizing L will help the algorithm to find final optimal parameters for the modified CNN network. How to transform from RGBD camera frame to the robot-based frame that I talked about with the simple model, which is the pinhole model. So first of all, they use the RGBD camera sensors to acquire Cartesian coordinates for arbitrary point. Then they implemented two different matrices, including the reference plane, based on the reference plane, which is TWR, and the TWC, R for the robot base and C for the camera base. And then the resultant transformation matrix from the camera to the robot base is actually the product between the R-based, the robot-based, and the inversion of the camera-based matrix. So in this project, in this research, they worked on multiple objects. As you can see here, this image is summarizing all the objects that they worked on for pick and pack operations. So as you can see, most of the objects that they focused on, like lime, greens, tomato, orange, onions, plate, potato, apple, sponge, banana. So all of these, most of them are having an average of 95% as accuracy of object detection, classification, and pick and place operations. However, as you can see here on the most right part of the diagram or the accuracy presentation, mushroom, unfortunately, is having less than 50% of accuracy. Why? Because of its shape, because of the change of color, because of the different poses that the mushroom can have, also the sensibility and the sensitivity of that of the object. So that's why mushroom is really considering a challenging research area, and that's why I'm interested in it. So challenges that we can face while designing an object, especially a 3D object detection system, first of all, is the multi-classing. So as I mentioned, when you work with a single class object detection system, it's much more, let's say, easier, less challenging than multi-class object detection. Also, especially in case of single or multiple classes, the multiple views that an object can have, the multiple poses, the multiple resolutions that an object can have within your data set can affect actually the output of your deep learning based model. So sometimes, for example, use ResNet inception towards object detection for a certain data set, and it will give you really high performance. However, when you use a different data set with different poses, different views, different resolutions, it might affect the output of that particular deep learning based model. Also, the efficiency and computational power is a key challenge in most of the deep learning based applications, and specifically for object detection, and particularly for mushroom as well. Occlusions, deformable objects, and interlaced object and background is also a parameter that affects and that makes the application more challenging and might affect the actual performance as well. And also the contextual information and temporal features that are involved in the application. There are so many other challenges that we as researchers can face for object detection in robotics and in object detection in general as well. Thank you very much for listening. I hope it was useful, it was enjoyable, and now I'm more than happy to take your questions.
Thank you very much, Zina, for once again a very good presentation. And I'm assuming everyone now is hungry, thinking on mushrooms, thinking on tomatoes, thinking on maybe a mushroom soup with tomato or tomato soup with mushrooms. And brilliant presentation as usual. Thank you very much, Zina. Now, everyone, if you have any questions that you would like to ask Zina, please feel free to use the question chat box to drop your questions, and I'm gonna read them to Zina to answer them for all of you. Feel free to drop your questions. We have quite a good audience today, so amazing, well done again, Zainab. And we're gonna go through the questions now. Again, thank you very much for everyone that's watching us, and I am pleased to let you know, Zainab, that your supervisor is amongst the audience. So anything that that went there is gonna ask you later. We have, I'm sorry if I mispronounce your name, Ihia Mohammed, saying thank you for the excellent presentation. And by the way, everyone, we're gonna have these recordings available in our BCS website after the whole presentation. Brilliant. Again, if anyone has any particular question that would like to ask that would for Zainab, we're more than happy to read them and provide those questions to Zainab as well. Zainab, in the meantime, while other people are probably writing their questions at the moment, it's really interesting again how those image processing algorithms, they can be used for mushroom and tomatoes, but can you go a bit deeper on the medical imaging processing and how the similar technique can be applied to, for instance, detecting early stage cancer? So do you think a technique such as this could also be used, let's say, for example, to detect early stage cancer, or to for medical image processing in lung cancer, for example? What are your thoughts on that?
Thank you, Jack, for your question. Obviously, object detection in general can be generalized for medical imaging as well, and particularly the area of research that I'm working on my PhD is to detect anomaly in images, like, as you truly mentioned, cancer in the lung cancer, tumor, or any other disease such as the DME disease that can be detected within the eye. And particularly with the eye image, it is a very sensitive and a very tricky kind of medical image processing because of its composition. because of the different features or different areas that can be involved into different diseases, and how your model will focus on particular area in the image that will actually help your object detection model to focus on that particular area and not be disrupted by other areas that you won't get the data from. So obviously object detection can 100% be useful for medical imaging, and yeah, it's really an important area for healthcare.
Awesome, thank you very much, Zainab. I have another question from E here. I wonder if you thought about using Xbox Kinect camera, since it can accurately measure the Z-axis distance between it and an object.
Yeah, you are absolutely right. Here we can use it for object detection because it will help into detecting the third dimension of the image, and will add value into the features that can be extracted out of your image, of course. For some reason, I can't see the questions like in a big way to know how, like very little.
Yeah, no, unfortunately, these to go to webinar has a very little window, I'm afraid, Zainab.
No problem.
But our next webinars are probably going to be on Zoom. We have already confirmed that from with the BCS, so it will be more interactive. So the audience will be able to turn on their cameras if they want and use audio and ask questions on audio. But this month's webinar will still be through GoToWebinar, and unfortunately, it's chat-based. But again, anyone in the audience that would like to drop your question, please feel free to do so. And Zainab will be more than happy to answer all of your questions. In the meantime, again, Zainab, another question I would ask you is what are your current plans in terms of the future and those techniques? I know you touched upon some of them, but if you would like to just comment on your current work and some of the things you're doing, some of the things you're hoping to do with this research in the future.
Thank you. So obviously, currently I'm focusing on my main PhD research, but I'm always like trying to keep myself up to date with the current research related to robotics, and especially anything related to vegetable pick and pack, pick and place operations. Because for me, it's really a challenging research area that I can't wait to start it really. It's going to be really exciting, and hopefully we can do something together in future.
Awesome. We have a question from Qbly. Thank you for your presentation, Zina. Really informative question. Can the mushroom problem be solved by multi-perspective image or simply two cameras capturing multiple perspectives?
Thank you, Qbly, for your question. So a multi-perspective or multi-pose of the image, of the mushroom image, can help the model to detect correctly detect the mushroom. But the problem, it can be the color, it can be the light on both sides of the mushroom, any background that the mushroom has from different poses that the camera can take the mushroom for, the contextual parameter the mushroom has to pick and place it, the sensitivity of the product, the mushroom also is a key that can decrease the performance of the model. But 100%, of course, using two different cameras from two different poses or perspectives would help the enhancement of the deep learning based model object detection outcome.
Thank you very much, Zainab. We have another comment/question from EE here. I'm also interested in robotics and image processing. could we collaborate on this topic? By the way, my current research area is about retinal image processing.
Yeah, of course. Please get in touch, Yahya. I don't know if you have my email. I think you have it on the description, but more than happy to post it here. So you can have my email and
Yeah. If you have it on your slide, Zainab, and you want to share it again with your contact information.
Yeah, I will type it on my slide.
In the meantime, we also have from Sumandeep. Thank you so much for the presentation. Truly insightful and knowledge enriching. Thank you.
Thank you, Suman.
We great. Nigel as well, and another very interesting presentation. Many thanks, Zainab. So brilliant, very engaging again, very good on numbers as well. Zainab, I think that is it in terms of questions. I just would like to mention, yeah, brilliant, Zainab. I just would like to mention everyone that we now have quite good talks in line, and the future webinars are going to include very interesting topics. We have two confirmed topics in the following webinars. One is going to be in green energy, and another one in email security, phishing, and ransomware. And we're going to have another one in artificial intelligence as well. So very good topics and very good webinars coming in future. So stay ready or looking into our emails and our events through the BCS. We have another one from Gabriella. Gabriella is asking or saying, thanks for the talk. Which would be the challenge you foresee on using multispectral cameras? From Gabriella.
Can you please repeat the question?
Which would be the challenges you foresee on using multispectral cameras? Oh,
yeah, thank you. So by using multispectral camera, the resolution problem can be involved. The multi-viewing again of the object is a problem. It's not always a problem, but it should be considered as one of the points that needs to be we need to make sure that it is there and it is well studied and well established in the build-up of the system. So multispectral camera can represent a challenge based on the challenges that I cited at the end, like multi-viewing, the multi-classing, multi-resolution, etc. Thank you, Gabriella, for your question.
Thank you very much, Zainab. I cannot see any more questions, so I would like to once again thank you very much. Thank you, Zainab, for your great presentation as usual. Thank you, everyone who has engaged with this lovely presentation. And once again, stay tuned in for the next webinars. We're going to be presenting a lot of very good stuff. And if you want to get in touch with Zainab or with the brunch, it's a pleasure to meet and talk to any of you. Thank you very much, Zainab.
Thank you. Thank you, everyone, for attending. Thank you, Tiago. Thank you for your questions, and hope to see you soon.